Welcome back to the Jungle Histology online training series. My name is Ken Longenecker, and this is the 6th of 9 modules designed to teach anybody who's interested how to use the methods my colleagues and I use to perform rapid reproductive analysis on coral reef fishes. The topic of this module is whether or not fish change sex. We're also going to take a look at oocyte development to try to get a sense of how frequently and how many eggs a female might spawn. This subject of sex change is particularly relevant for coral reef fishes. As of 2008, sex change was confirmed in 27 fish families, and it turns out that most of those families occur in tropical marine habitats. In other words, the same sort of habitat where you would find a coral reef. Sex change is important to reef fisheries management because the managers of these resources are going to want to be sure that rules and regulations aren't causing the fishing down of one sex over another. In other words, managers are going to want to be sure that there's an appropriate balance of sexes in a population. Let me give you a couple of terms. Hermaphroditism is the reproductive mode for species that change sex as a normal part of development. A species that's a sex changer is called a hermaphrodite. Gonochorism is the reproductive mode when a species does not change sex over its lifetime. A species that doesn't change sex is called a gonochore. And here's a couple of subcategories for hermaphroditism. Protogeny is the reproductive mode for a species that changes from female to male. Protandry is the reproductive mode for a species that changes from male to female. So a protogynous hermaphrodite is a species that changes from female to male, and a protandrous hermaphrodite is a species that changes from male to female. Well, how can we tell if a species changes sex? We focus on the criteria outlined by Sadovi and Shapiro in this important paper published in 1987. Here are 3 pieces of evidence that we look for. These are listed in order of increasing certainty of sex change. The first is a bimodal size frequency distribution. That is, one sex is larger than the other. A bimodal size frequency distribution would suggest to you that perhaps the species changes sex. We're going to come back in the next module and see that these bimodal size frequency distributions exist in gonochoristic species as well. So a bimodal size frequency distribution does not mean that a species changes sex. However, it suggests to you that you should take a closer look. The second criterion we'll look for is only relevant for protogynous species. This is when there's a membrane-lined cavity, often called the remnants of an ovarian lumen in the testes. Now, the ovarian lumen is just the space where oocytes are shed prior to being released into the water column. As a species changes sex, this cavity often remains in the testes. So it's good evidence that the gonad has changed from having an ovarian function to having a testicular function. Of course, we don't see this in the opposite case, that is, in protandrous species, because that ovarian lumen would not exist in a testis. And finally, the key piece of evidence that we're looking for is the existence of transitional individuals. That is, a gonad that has both male and female gametes. And we've seen examples of that in the previous module. Let's take a look now at how you would evaluate your data to determine whether or not there is a sex-based bimodal size frequency distribution. The Ttest showed us that females were smaller than males, and this would suggest that if the species is a sex changer, it starts first as a female, then changes to a male. That is, that it would be protogynous. This is one of those cases where you would expect to see a lumen in the testes. So let's see what the lumen looks like in the ovary first, and these arrows point to that empty space in the ovary into which the eggs are shed before they're released into the water column. Here's a mature male of the same species at the exact same magnification, and you can see that you have those empty spaces in the testes as well. The presence of this lumen in the testes would suggest that we do have a protogynous species. And for comparison, let's take a look at the testes of a non-sex changing species. This does not have a lumen. The arrows are pointing to some empty spaces in there, but these are small tubules that go through the testes. They have a much different form than the lumen in the last slide, where that empty space spanned the whole slide. And finally, we can diagnose sex change if we have individuals with transitional gonads, that is, gametes of both males and females in the same organ. And here we have the male gametes in circles and female gametes indicated with the arrows. So we had smaller female size, we had the presence of a lumen in the testes, and we have transitional individuals. So this would be diagnostic of a protogynous species, that is, females changing to males. What will we be looking for protandrous species, that is, males changing to females? Typically the males would have a smaller average size. You would not see that lumen in the testes, but again, you would see the transitional individuals. One final point I want to bring up about diagnosing hermaphroditism or sex change is that these transitional gonads can occur in non-sex changing species. There can be some developmental mistakes, there could be some environmental impacts, even perhaps the influence of toxins may cause one or a few abnormal individuals that have both male and female gametes in the same gonad. What you're going to be looking for as evidence of sex change is a relatively high frequency or a relatively high proportion of transitional individuals in the population that you're looking at. While you're looking at these slides to evaluate sex change, you should also be taking a close look at the ovarian sections to evaluate oocyte development. And this gives us a little bit of a clue about how frequently a fish spawns and how many eggs a female may be releasing each time she spawns. We have three types of oocyte development that we're going to talk about. One is asynchronous. That's when you find a whole smattering of all the different possible egg stages in the same ovary. And there are no distinct groups or no distinct size classes of eggs. This would suggest that the females are what we call trickle spawners. That is, just releasing eggs really frequently but in very small quantities. Another type of oocyte development we see is called group synchronous. Here you would see several stages of eggs in the same ovary, however they would occur in size classes. You would see one batch of similarly sized small eggs, you would see another batch of similarly sized medium eggs, and then you would see another batch of similarly sized large eggs. This would indicate that the females spawn somewhat frequently, however, they would release their eggs in batches rather than letting the eggs trickle out daily. And finally, we see synchronous oocyte development. This would be when all of the eggs in a mature ovary are basically the same size and suggesting that all of the oocytes are released en masse. Those are the three types that you may see. However, we should say right now that the only type of oocyte development we've seen so far in the reef fishes that we've been examining have been group synchronous. So unfortunately, this is the only example that I can give you, and let's take a look at those now. Here's a section through the ovary, and what you can see is that there are different classes of eggs. The other thing that you're trying to evaluate here is whether there are size groups of eggs. This can be a little bit harder to evaluate because not all of these oocytes are sectioned right along their midline, but if you look carefully you can get a sense of whether there are different groupings of egg sizes. For instance, the black circles show some stage 1 oocytes, and if you look around this section you can see that most of those stage 1 oocytes are just about this size. The yellow circles are around some stage 2 oocytes, and again, if you look around this section, you can see that basically all the stage 2 oocytes are about the same size. And we see the same pattern for stage 3 oocytes circled in red here. So what we see in this slide are three classes of oocytes and three size groupings of oocytes, which would indicate to us that this is a group synchronous spawner. What that means is that this species probably spawns several times per reproductive season. This concludes Module 6. I'd like to thank our funders